Testing, can you hear me? Testing again, can you hear me? Okay, testing one last time. Alright, this video is public now. So this is going to be my last Openstax Calculus 3 stream. There's only one chapter remaining in this book. Yeah, so Calculus Volume 3, one chapter remaining, and then like after I'm done reading this, uh I will read some other calculus. I do have the intention of reading other calculus books. I won't just end here because I do need practice. Like I have knowledge of the topic, but I'm still not good at solving the equations. Anyway, so I learned about second order linear equations and the non-homogeneous linear equations. Um, the non-homogeneous part, it takes so long to solve this. Even the normal linear ones, they take so long to solve. So I'm going to read about the applications. Maybe the methods would be more cemented in my brain. Should I just open these? Is there a chapter? Okay, let's see. Key concepts. Let's see, is there a summary here? Second order. Uh, no, I don't. Okay, this summary is not good. I'll just open this chapter. I keep that chapter open and I'll read about the applications. So first one, simple harmonic motion. Consider a mass suspended from a spring attached to a rigid support. Gravity is pulling the mass downward and the restoring force of the spring is pulling the mass upwards, as shown in figure 7.2. When these forces are equal, the mass is said to be at the equilibrium position. If the mass is displaced from the equilibrium, it oscillates up and down. This behavior can be modeled by a second order constant coefficient differential equation. So we have the natural position, we have equilibrium, mg is equal to ks. The force, the upward force by the spring on the mass, the spring is pushing the mass upwards and it's proportional to the distance. So that's why we have ks over here. And in motion. Oh, this is the equilibrium position. So the weight of the mass cancels out with the upward force. So mg is equal to ks. And then from this equilibrium position, they decided to make this x is equal to 0. So x is the displacement from the equilibrium position. Let x denote the displacement of the mass from equilibrium. Note that for spring mass systems of this type, it is custom to adopt the convention that down is positive. Okay. Thus, a positive displacement indicates that the mass is below the equilibrium point, whereas a negative displacement indicates the mass is above. Displacement is usually given in feet in the English system or meter. I think we should just stick with meters, right? Why do we have feet? So gravity is 9.8 meters per second square. According to Hooke's law, yeah, it's proportional. The restoring force of the spring is proportional to the displacement and acts in the opposite direction from the displacement. So the restoring force is given by minus k s plus x. The spring constant is given in pounds per watt in the English system and in newtons per meter in the metric system. Now, by Newton's second law, the sum of the forces on the system is equal to mass times acceleration. So we have mass times acceleration is minus k sx plus mg. Hold on a minute. So the acceleration downwards is positive. It's it's accelerating backwards, right? So we have, okay, so the downward force is mg, the weight, mg, the weight, and the upward force is minus ks plus x. So s is this, x is this. Okay, that makes sense. And the acceleration, so the net force causes the acceleration and it accelerates upwards. The acceleration is negative, right? We have this. However, by the way we have defined our equilibrium position, mg is equal to ks, the differential equation becomes m times acceleration of x plus kx is equal to 0. Um, hold on a minute. It is convenient to rearrange this equation and introduce a new variable called the angular frequency, letting angular frequency be root k over m. We write this equation as root k over m. Oh no, what are they doing? Angular frequency square. Where did this? Hold on. It's convenient to rearrange this equation and introduce a new variable called the angular frequency. If I divide both sides by m, I get acceleration plus k over m, x is equal to 0. K over m, I can define that as omega. But over here, they define omega as root k over m. This differential equation has the general solution. Uh, okay, where did they get has a general solution? Cause hold on. If we have a homogeneous linear equation, like they do, then they want a general equation of the form e to the power of lambda x. Is this just a estimate? If we plug this in, it will work. Okay, so this gives the position of the mass at any point in time. The motion of the mass is called simple harmonic motion. The period of this motion is t is equal to 2 pi over omega. And the frequency is omega over 2 pi. Assume an object weighing 2 pounds stretches a spring 6 inches. Find the equation of motion if the spring is released from the equilibrium position with an upward velocity of 16 feet per second. What is the period of the motion? Spring is released from the equilibrium position with an upward velocity of 16 feet per second. What is the period of this motion? Okay. Let's see. Example 7.17. Oops. So, so we have uh the differential equation becomes m double derivative of x and then we are going to write omega x, where omega is, I will just write it here. C1 cos omega plus C2 sine omega. So there we have this, and then the uh period is 2 pi over omega. So mass is this. We don't know what K is. You know, X is 6 stretches a spring 6 inches. Uh, Assume an object weighing 2 pounds stretches a weight 6 inches. So S is equal to 2. Hold on, I'm getting confused. So this is one equation. Another equation is this other one, right? The mass acceleration is equal to minus k s minus k x mg. We have g, we have m, and then they said x. They gave us x. Uh, they gave us the velocity, but they did not give us the acceleration. Assume an object weighing 2 pounds stretches a spring. No, this is S. We have S. 2 pounds is this. And the spring is released from the equilibrium position. Spring is released from the equilibrium position. Wait, what? Spring is released from the equilibrium position. So they removed this object. With an upward velocity of 16 feet per second. MJKS. Okay, MG, I understand. The equilibrium position is like this. MG, I understand. S is 6 inches. To how did they get half here? Stretches a spring 6 inches. So 2 times, where is it? 32. 2 times 32 divided by, and this inches and feet is confusing me. This is half a feet. 2 times 32. Uh, I don't like thinking. I want the metric system. 2 times 32 is 64. Why did they say 2? How is the force measured? In how's the force measured in this system? Pound. Okay, let's just mark it as 2. Is it in tons? No, I don't think that makes sense. We have this weight equal to mg. Mass is 1 over 6. But we have the mass, no? Wait, we reduces the mass. Weighing 2 pounds. Oh, this pound over here is newtons. This is not mass. This is newt. Okay, okay. Pound. The force is measured in pounds. I forgot that. This pounds here is not mass. It's force. Yeah, that changes things a lot. So 2 times k s k is 4. Um And then the weight is equal to mg. The weight is 2 pounds. Pound, pounds, then meter, then feet second squared. But then what is this measured in? If the force is pounds, what's the mass? Mass 116. But what's the thing? Yeah, they should have been in the other system. I don't know what the is the mass also pounds? So the downward force is equal to mg. We have m, we have k. We plug it in here. We can find w. We have the velocity. It wasn't even needed. What is the period of the motion? Was the velocity not needed? So we have this. We can just find omega and find the period, right? Period of this motion is pi over 4. Pi over 4. So, wait. Omega is equal to k over m. K is 4. M is 1 over 16. So we are left with 1 over 4, which is 1 over 4. 1 over plus minus 2, right? 1 over plus minus 2. Period of this motion is 2 pi over 8. K is 4. 4 divided by m. Mass is 1 over 16. I'm doing this wrong. 4 divided by 1 over 16 is 64. Square root that, we get plus minus 8, right? So omega is plus minus 8. Then how do we, is period always positive? Yeah, it is, right? Seconds. So 8 over here. We didn't need the velocity. So why are we using the differential equation? Okay, never mind. Writing the general solution in the form this has some advantages. It is easy to see the link between the differential equation and the solution, and the period and the frequency of motion are evident. This form of the function tells us very little about the amplitude of the motion. However, in some situations, we may prefer to write the solution in the form a sine omega t plus phi. Although the link to the differential equation is not explicit in this case, the period and frequency of motion are still evident. Furthermore, the amplitude of the motion a is obvious in this form of the function. Constant phi is called a phase shift and has the effect of shifting the graph of the function to the left or right. To convert the solution to this form, we want to find values of a and phi such that this is equal to this. We apply the trigonometric identity to get this. Thus, C1 is a cos phi. Square both sides, we get a squared. Thus, a is equal to this. Since tan phi is this. To summarize, the function this can be written in this form where a is this square root, where a square is c1 square plus c2 square, and tan phi is c1 divided by c2. We must take care to ensure phi is in the right quadrant. Express the following functions in the form. What is the frequency of the motion and amplitude? Okay. I'll just look at the answer for this one. So A square this, 1 square root, and then wait a minute. C1. Okay, okay. Tan phi is C1 divided by C2. Hold on. Cos and then sine. C1 divided by C2. C1 divided by C2. Yeah, that makes sense. With the model just described, the motion of mass continues indefinitely. Clearly, this doesn't happen in real life. In the real world, there's almost always some friction in the system which causes the oscillations to die off slowly, an effect called damping. So now let's look at how to incorporate that damping force into our differential equation. Physical mass spring systems almost always have some damping as a result of friction, a resistance, or a physical damper called a dashboard. Because the damping is primarily a friction force, we assume it is proportional to the velocity of the mass and acts in the opposite direction. So the damping force is given by minus bx minus b derivative of x. Um, for some constant b. Okay, why did we need the minus? I mean, the minus could have just been part of b. Again, applying Newton's second law, the differential equation becomes this. Oh, that's why I put the minus out. Then the associated characteristic equation becomes this. Applying the quadratic formula, we have this. The b squared is more than 4mk. In this case, we say the system is overdamped. The general solution has the form this. Behavior of overdamping spring mass system with no change and only one change in direction. Both alpha 1 and alpha 2 are less than 0 because the exponents are negative. The displacement decays to 0 over time, usually quite quickly. They're using pounds and feet again. I will just read this through because I'm not used to their system of doing things. B square is equal to 4mk. In this case, we say the system is critically damped. General solution has the form this where alpha 1 is less than 0. The motion of critically damped system is very similar to that of an overly damped system. It does not oscillate, however, with critically damped systems. If the damping is reduced even a little, oscillatory behavior results. From a practical perspective, physical systems are almost always either overdamped or underdamped. It is impossible to fine tune characteristics of a physical system so that B square and 4mk are exactly equal. So, figure 7.7 shows what typically critically damped behavior looks like. All right. Oh, now they have right the right system. So 7.20, what they say copy, paste. 1 inch mass stretches a spring 20 centimeters. The system is attached to a dashboard and imparts a damping force equal to 14 times the initial velocity of the mass. Find the equation of motion if the mass is released from the equilibrium with the upward velocity of 3 meters per second. So damping force is usually given by minus bx square. So the force of the damping is minus b derivative of x. Means we find the equation of motion if the mass is released from equilibrium with the upward velocity of 3 meters per second. 14 times the instantaneous velocity of the mass. Imparts a damping force equals to 14 times the instantaneous velocity of the mass. So should I write minus 14 or positive 14? B is equal to 14. Downwards, wait, that's the dashboard that imparts a damping force. I think it would be better if it's okay. Let's try b square minus 4mk. B square minus 4. 4mk is 4mk. We know m. Do we know k? Spring mass. 1 kg is mass stretches a spring 20 centimeters. mg is equal to minus ks. Right? Is it minus ks? Because ks is upwards. Where is it? mg is downwards. Ks. Is k negative? Forget it. Ks. 9.8. I'll take g is 9.8 because that's what they give. And then the length is 20 centimeters, but that's 0.2 meters. No, that's 0.1. Yeah, that is 0.2 meters. Now is k is k is 9.8 divided by 0.2. 49. K is 49. Um, this force is the upward force. So the upward force is minus ks, right? Now, okay, then we have, I'll just hide this. Then we have 4mk is 4mk is 49 times 4, 169. Wait, 196. 14 square is also 196. So this is the second case where what do we call this case? Critically damped case. The general solution has the form xt. What are we trying to find? equation of motion. Xt C1 and then C2 T E alpha 2 T E alpha, well, it's the same alpha. E alpha 1 T E alpha 1 T Xt is equal to E alpha 1 T. What do I do with this information? Okay, so 14 square down to differential equation becomes mx plus bx plus kx. K we know, M we know, B we know. Hold on, it's that. Is that the answer? This is the motion then. Time to variation. Is this it? This is the equation? Then what do they want us? XD. Oh no, they want. Okay, okay. No, I got this wrong. So alpha, there's only one alpha, is equal to minus B. That this is 0 over 2A minus 14 divided by mass is 1. So we have minus 7. Minus 7. Minus 7 as. Wait, let me see the. No, not here. Minus 7. Okay, that's done. What do I do with this information? And when t is equal to 0, x is equal to 0. So C1 is 0. Yes. X 0. This is 0. This is 0. Is equal to C1, which is 0. Which implies and what else do we know? Find the equation of motion if the mass is released from equilibrium with an upward velocity of 3 meters per second. Mass is released from equilibrium. I don't get this. What this statement means. Mass is released from equilibrium. So the equilibrium is when the two forces are equal, right? This is equilibrium. Mass is released from the equilibrium. So if I take the mass away, the spring goes up by 3 meters per second. Is that what they're saying? Or are they saying that this mass is going up and down, but when it reaches the equilibrium, it's going up by 3 meters per second? The if this is the case, then the derivative of x is c2 uh t minus 7. And when this is 0, oh wait, this being 0 also does not make sense. No, no, because my derivative, this is wrong. I'll take c2 out and I will differentiate this. So derivative of the first times the second plus the first times the derivative of the second. There. And then when we do this 0, we get c2 e minus 7, but this is becomes 0. This becomes 1, I mean. 1, 0, so we are left with c2, which is 3 meters per second. Why minus 3? Derivative of x. Why is it minus 3? Derivative of the first times the second plus the fourth times. Why is it minus 3? What is the equation? What is their equation? 14 plus 49. 114, 49. Just the general solution. Initial condition x0 is equal to 0. So c1 is 0 and then the derivative of x. Since c1 is 0, I can write this and then it's not clear to me why it's minus 3. Upward velocity, okay. Okay, then that makes sense. Minus 3 meters per second. Okay, b squared is less than minus 4 mk. In this case, the system is underdamped. The general solution has the form this, where alpha is less than 0. And then damped systems do oscillate because of sine and cosine terms in the solution. However, the exponential term dominates eventually, so the amplitude of the oscillation decreases over time. Note that for all damped system, limit as x approaches to xt, where t approaches to infinity is 0. The system always approaches equilibrium position over time. Isn't it the same for every system? But simply move back to the equilibrium position. Overdamped, critical. Okay. With these two cases, case 1 and case 2, they just go back to the equilibrium position. Case 3, it does oscillate, but this as well will go eventually go back to the 0 position. And they're using the pounds and feet again. Yeah. Landing vehicle. Forced vibration. What other? Okay, the RLC series circuit. The last case we consider is when external force acts on the system. This case, the motorcycle suspension system, for example, bumps in the road act as an external force acting on the system. Another example is a spring hanging from a support. If the support is set in motion, that motion would be considered an external force on the system. Model these force systems in the non-homogeneous differential equation. An external force F is represented by the Ft term. As we saw in non-homogeneous linear equations, differential equations such as this have solutions of the form um okay where this is the general solution to the complementary equation and xp is a particular solution to the non-homogeneous equation. If the system is damped, then limit st goes to infinity is 0. Since these terms do not affect the long-term behavior of the system, we call this part of the solution transient solution. Long-term behavior of the system is determined by xp, so we call this part the steady state solution. Um, okay. And this is where you use the non-homogeneous one, right? I will get back to this later when I study about later when I study physics in my other channel. Consider an electric circuit containing a resistor, an inductor, and a capacitor, as shown in figure 7.10. Such circuit is called an RLC series circuit. RLC circuits are used in many electronic systems, most notably as tuners in the AM/FM radios. The turning knob varies the capacitance of the capacitor, which in turn tunes the radio. Such circuits can be modeled by the second order constant coefficient differential equation. The I denotes the let I denote the current, Q denote the charge of the on the capacitor, L denote the inductance in henries, R denote the resistance in ohms, C denote capacitance in farads. Lastly, let E denote electric potential in volts. Kirchhoff's voltage rule states that the sum of the voltage drops around any closed loop sum of the voltage drops around any closed loop must be zero. So we need to consider the voltage drops across the inductor, the resistor, the capacitor. Because RLC circuit shown in figure 7.10 includes a voltage source E, which adds voltage to the circuit. We have EL plus ER plus EC is equal to E. So the voltage drop when it goes through the inductance, the resistor, and the capacitor is equal to the total voltage. We present the formula as below without further development. Those of you interested in the derivation of these formulas should consult a physics text. Using Faraday's law and Lenz's law, the voltage drop across an inductor can be shown to be proportional to the instantaneous rate of change of the current with the proportionality constant L. Thus, En is L derivative of I over T. Next, according to Ohm's law, the voltage drop across a resistor is proportional to the current passing through the resistor. Last, the voltage drop across the capacitor is proportional to the charge Q on the capacitor with proportionality constant 1 over C. Thus, EC is equal to 1 over CQ. Adding these terms together, we get L. We get this. Noting that I is dq over dt, this becomes it becomes like this. Mathematically, this system is analogous to the spring mass system we have been examining in this section. So find the charge on the capacitor in an RLC series circuit where L is this, R is this, C is this, and E is this. Assume the initial charge on the capacitor is 0 and the initial current is 9 amps. What happens to the charge on the capacitor over time? Copy. $7.24. Um, so this is the equation. L is equal to, I like this format of the equation. Double derivative U plus R Q plus Q is equal to ET. What happens to the charge on the capacitor over time? Find the charge on the capacitor in an RLC circuit. Charge on a capacitor. So EC is equal to 1 over CQ. The charge on a capacitor is this. Now what? What happens to the charge on the capacitor over time? Assume initial charge is 0. So E0 is Q0, 0. But that tells us nothing. Initial capacitance is 9 amps. What happens to the charge, the capacitor over time? So this is a homogeneous, non-homogeneous equation. First, we want to find the thing, the, what do you call it? Hold on, I forgot what you call it. Like equating it to 0. Complementary equation. First, we need to find the solution of the complementary equation. That gives us, that gives us, mm, that gives us this. And then we find the potential equation. And then we get a general solution. But what are we trying to find? Hold on, let me just see the first step. EQ, yeah, we have that. They plugged in the equation. Hold on, let me just plug in the numbers myself. And we don't need that. So L is 5 over 3. R is 10. C is, I don't know. C is 1 over 30. 1 over, I should just write 30 here. And then this is 300. Then what is, then then they want, we need to find this, right? Hold on. Oh yeah, they divided it. General solution to the complementary. Okay. Hold on. 5. Actually, yeah, let's just divide it. Let's divide it first. Divided by 5. Hold on. Wait. What happens to the 3? No, I'll just multiply the 3 later. Wait, they multiplied 3 as well? Okay. Yeah. 6, 18, 180. Now we need to find the solution for this. Square plus 6 lambda plus 18 is 0 minus p plus minus p square minus 4ac. What's 18 times 4? 72. I'll just subtract 72. Wait, don't I get, hold on, 72. Thing is, if I have minus 72, e square minus 4 times a times c. But I have complex solution, right? How did they get this? Wait. Let me check the thing. It's a complex conjugate. No, the other one. So it's plus minus 6i. Right. This is what? 72 over 2 minus 6 plus minus 6 I over 2 minus 3 plus minus 3 I So then the solution becomes then Q T is equal to alpha and beta e to the power of minus 3x C1 cos beta. Well, actually, it's t, not x. Plus C2 sine 3t. Then we need to find QP. I forgot how you find QP and a non. So QP, let's go here. So when we do find a solution, what do we do then? Yeah, how do we find YP? Initial guess for YP. So if it's QT is in this form, QT is yeah, in this form. The initial guess of YP is A e to the power of, okay, taking e to the power of alpha x out, and A and B is what? Um, this does not make sense. A, B, beta, alpha. But alpha and beta are both 1. No, alpha and beta is what we are trying to guess. So, yeah, but that's C1 and C2. Is that what they want us to do? Okay, let me think about this. A, E, cos 3t plus B, E, sine 3t. And when it's 0, when it is 0, then the final answer should be 0. This is 1. This is 1. Uh, cos 0 is 1, right? Sine 0 is 0. So A is 0. So we are just left with B e to the power of minus 3t sine 3t. Initial current is 9A. and we derivate this potential solution. Uh, yeah. This derivative of the first times the second plus the first times the derivative of the second. If I do the initial current, so then t is equal to 0, this becomes 1, this becomes 0. We are just left with -3, right? Yeah. B is equal to -3. So our final solution is -3 e to the power of -3t sine 3t. And that's wrong. Okay, let's see. A is 10. QP is equal to A. Form Q, where A is a constant. Okay, I have no clue what just happened. So I know how they got the this far. Assume a particular solution of the form QP is equal to A. But why though? Oh, because this is a constant. So okay. Q, so this wasn't needed. So QP, we assume it's an A, but when T is 0, current is 0. Sorry, initial charge on the capacitor is 0. So when A is using the method of undetermined coefficients, we find A is equal to 10. Undetermined coefficient. Substitute yp into the differential equation. Substitute A into the differential equation. So A over, okay. Hold on. So I take all of this. But what I don't understand, if you plug in 0, the charge should be 0, right? So shouldn't A be 0? Q A Q B derivative is 1. Double derivative. No, derivative is 0. So what am I doing? Derivative is 0, yeah. So double derivative is 0. 0, 0. (180), which implies that A is equal to 10. If QT is equal to 10, then explain to me how when I plug in T is equal to 0, I don't get 0, instead I get 10. We get A is 10. So QT, potential solution, add the general solution to the complementary equation and a particular solution you just found to obtain the general solution to the non-homogeneous equation. Okay. I still don't understand the why this thing works. This is yeah. C1 cos 3t C2 sin t plus 10. Applying initial conditions Q0 is equal to 0. And now we apply the conditions. So this is 1. Got 10 over here. Sine 0 is 0. C1. C1 plus 10. Right? Minus 3 e to the power of minus 3t. Derivative of the first times the second. We need to find the charge. And yeah. So it's this entire thing minus 10. Derivative of the first times the second plus the first times the derivative of the second. Cos becomes minus sine. We are multiplying it by 3, so it becomes 30. C2 sine et. And this becomes cos. If t is 0, then this is the answer is 9. So 9 is equal to, plug in 0 here, we get 1, plug in 1. We're left with minus 3. Sine 0 is 0, sine 0 is 0. This is 1. Okay, so minus 10, 1. And then that's it, right? Plus, this is 1. 3C2 is what we are trying to find. This is 1. $30 plus 3C2. C2. Okay, first we divide both sides by 30 by 3. C2. Is this even correct? C2 minus 7. Yes. Um, let's see. So this becomes C1 negative 10, C2 minus 7, negative 10 minus 7. Okay. I guess when I'm studying physics later, studying electricity, this will make it easier, but it's not clear to me why it works. Using power series to solve first order and second order differential equations in the introduction to power series, we studied how functions can be represented as power series. Uh, yeah, okay. We also saw that we can find series representation of the derivatives of such functions by differentiating the power series term by term. So we have, okay, and the double derivative is this. In some cases, these power series representations can be used to find solutions to differential equations. Be aware that this subject is given only a brief treatment in this text. Most introductory differential equation textbooks include an entire chapter on power series solution. This text has only single section on the topic. So several important issues are not addressed here, particularly issues related to existence of solutions. Examples and exercises in this solution section were chosen for which power solutions exist. However, it is not always the case that power solutions exist. Those of you interested in more rigorous treatment of this topic should consult the differential equation text. Introduction to power series. Okay. Wait, hold on. I can't remember properly. Did they say every function can be represented as a power series? Okay. Series solution to differential equations. Find power series solution for the following differential equation. Yes. the- Assume differential equation has a solution of this. Differentiate power series term by term to get this and this. Substitute power series expression into the differential equation. So this minus this. Hold on. Example 7.25. Wouldn't there be, wouldn't like most of the terms cancel out? 7.25. So they said y double derivative minus y equal to 0. Okay, let's just try this one. So they said yx is equal to sum to infinity from n is 0 to infinity. Now we are differentiating it once. Infinity. So n a n x to the power of n minus 1. Um, but if it's just x, what about n is equal to 0? If we differentiate the first term, the first term will disappear, right? Yeah, yeah, yeah. So this minus this is gives 0. So what they're saying is that this minus this gives 0. So then that means if I bring this to the other side, I get this. Uh what about the first two terms? So then the first two terms don't exist, right? Maybe they do. No, they do actually, because this is n minus 2. This here is n minus 2. So that means if I match all the x to the power of I terms, then I have n minus 1 a n is equal to a n, right? Or wrong? No, that's wrong. Wait. So if I plug in n is equal to 2 over here, I get x to the power of 0. If I plug in n is equal to 0 over here, a0, I get x to the power of 0. So the matching terms will have, it will be okay, yeah, it will be like this, right? No, I think I'm getting this wrong. Because an over here at 0. No, an over here at 2 should match with an at 2. If I plug in 2 over here, I get a2 next to the power of 0. If I plug in 0 over here, I get a0 x to the power of 0. X to the power of 0 and x to the power of 0, they match. But then a2 and then there is a0 here. So I have to add 2 here. Isn't that right? Find the power series solution. So then that means can plug in this back here. That means I'm doing this the first time, so I might be completely off. X to the power of n minus 2. What's bothering me is if this is plus 2 or minus 2. N is 0, a0, x0. N is 2, a2, x 0, a2, x0. So a2, A0. Um, yes, I think that's right. So then this minus this. Is that it? I'm doing this the first time, so I have no clue. This minus. Is it this? Is that right? Um, Let me see what they're doing. This, then oh, they wrote it in terms of 0. N is equal to 0. 0, 0. Yeah, writing in terms of 0 is easier actually. I write it in terms of 0. But then, okay, let's just write it in terms of 0. Uh, we have 0. We'll just write N instead of, hold on. Then I will increment this by 2. Increment N by 2. Increment N by 2. And this is what they did, right? Um, yes. And should I put this back in here? So this minus this gives 0. But then where do I go from there? And then, okay, I take the summation out. They took x to the power, wait, because power series expansion of functions are unique, this equation can only be true only if the coefficient of each power of x are 0. So if we have this for n, this recurrence relation allows us to express each coefficient a n in terms of coefficient of 2 terms earlier. Um, in order for this to be 0, in order for this minus this to be 0. So at x to the power of 0, the coefficient must be equal. At x to the power of 2, the coefficient must be equal. At x to the power of 3, the coefficient must be equal in order for the final sum to be 0. So, okay, I get what they're saying. So this should be equal to this. Isn't that what I was doing earlier? But then what? This is the solution? 4 factorial, 6 factorial. Recurrence relation. Ah, so yx. How did they get? So A2 is if I plug in 0, A0 is equal to A2. Okay, let's do it in reverse. A0 is equal to A2, 3, 0. Actually, just 2. I'm plugging in. And then I have plus 2, so 3. 3 times 2. Then A1 is, sorry, A2 is plus 2 plus 2, 2 plus 1. 3 plus 2, 3 plus 2, 3 plus 1. So instead of A3, I can write this A looks like a D. So A 4 times 3. 5 times 4. So the pattern here is 5 times 4, 3. So the pattern here is n, A n minus 2 over n factorial. But what is the base case? Involving odd n. Wait. Odd n. If n is odd, then the base case is A1. If it's even, the base case is 0. That's what they're saying. A0, A1, 0 over 2, A1 over 3 factorial, 0 over 4 factorial, A1 over 5 factorial. This solution, okay. Okay, I think if I want to read about power series, I will read a separate book. Answer key. Okay, I think after this chapter, this is it. There's nothing after. So, yeah, I read Calculus 3, but I'm not like fully in depth. I will have to read another book for that. But I did finish, at least getting a base understanding of it. I did finish reading it. I want to indulge more in the proofs. So what books do they have? I think my other series is about data structures and algorithm, and I think after I finish that book, I'll start with some probability and statistics book. If you guys know a very good probability and statistics book, do let me know. Because I do find mistakes in some of these books. And yeah, so that's the end of this section. Anyways, see you guys next time then. Bye.